Hello everyone. Hi, my name is Sriranga Kulkarni. I am a technology professional working in software engineering field. I also have completed my masters in knowledge engineering from National University of Singapore, which deals with applying tools and techniques in extracting knowledge from raw data, which can be further used to make some effective decisions for solving certain business problems. Thank you, back team, for allowing me to have a presentation on application of CRISP-DM different stages, a walkthrough via sample project. You can contact me at sriranga.kulkarni@gmail.com for any feedback or queries, and also alternatively you can connect me at my LinkedIn profile. So yeah, let's start then. Yeah, so we wanted to help the mind of a smart trader for making better trades by using good data and robust models so that they can take informed decisions. So this was our final year MTech project under PyQuant Global Private Limited, which was a Singapore-based investment trade company, and Waiming, Nataraj, George, Elizabeth, and myself, Sriranga, were the teammates of this project. It was conducted for 1 year actually. So yes, we wanted to help the management team or the decision maker team for better investment. So yes, so here's the agenda. We will be going through the objective and scope, the solution outline and the benefits, and the problem domain, the business understanding and the data understanding steps of CRISP-DM, which is a domain familiarization and knowledge acquisition, which is like an iterative process as we have explored in the previous session. And the architecture, we'll go through briefly about how we made it a system, how we integrated all the models and the data behind analysis and the results and the visualization under a one umbrella to make it a one system. And the data modeling approaches that we went through, the methodology that is CRISP-DM, and the data understanding and pre-processing process, the modeling and the evaluation and the comparison, all the theoretical aspects that we went through the previous session. We were going to have a look at a sample example via this project Smart Trader. Of course, the results demo I may not be able to show in this session, but we will definitely see the results in the conclusion. So, business goals, objectives and scope. So to build a dynamic and robust US stock trading system based on a multi-factor model that is systematic, rigorously and carefully tested across time. Actually we tested from 2004 I think, and thus giving consistent and profitable returns in real life that can closely match the back test, while both long and short positions would be considered, combined wherever possible, which features the whole system features are customizable, which is catered to the user's risk profile and style preference in terms of various factors, metrics, leverage the number of stocks chosen by the users, and the performance, since it's processing of large data set, that is the stock inverse data set SP500. So it has a lot of data, so the performance of the tool is also be under consideration, and also how well we incorporate the knowledge engineering and computational intelligence techniques, that is KE and CI techniques, to boost the performance as much as possible while still keeping the intuitive and agreeable factors in place. So what are the business goals in terms of solution and benefits? So we want to implement an intelligent knowledge-based system with the capability of generating a portfolio of US stocks information on any particular day based on the S&P 1500 universe of stocks, which helps in assisting the traders and the portfolio managers at PyQuant to make informed decisions on potential stock selection to generate their desired return, and which will help to empower the processor analyze large data sets that we have and realize non-linear decision making by leveraging computational intelligence, enable to learn and adapt over time autonomously and proactively, and help to respond timely and readily for dynamic and equivocal situation. So these are the few benefits we are going to derive from implementing this system. So this is the first step of identifying the benefits or the business goals in CRISM-DM. Now comes the data and business understanding. So we wanted to analyze, or what are the stakeholders, who are the stakeholders in terms of data and business understanding. The first comes the who, the domain experts. We consulted the stock, investment, trading, consultants, experts, which who are in the stock domain, and the lecturers on how to conduct or do the data understanding or business understanding. Thank you for, and also the online resources. So these were the guys who interacted with. So this was part of the who part. And then when actually the domain understanding, that is data and business understanding, right? It is actually the main part, the initial phase of the domain familiarization, and we had multiple milestones, and then we used to review every milestone. What are the current situation, what is the next target of acquiring the knowledge, and then what are the drawbacks or the merits and the demerits of advantages of the current techniques that we are using to analyze the data or business data understanding, and any ad hoc and informal communication over internet or in person with the domain experts. So what exactly we are trying to understand? So data and business understanding deals with understanding the underlying domain or the problem we are trying to solve, or the related domain or the problem we are trying to apply the business the knowledge, the CRISP-DM methodologies on. So in our case it was a stock data. So the domain experts we consulted was very experts on stock investment strategy and tactics. The lecturers helped us in determining the scope, to what extent we need to understand the data, or what level we need to go and study, and the requirement and the feasibility, whether this smart building of smart trader is feasible in 1 year timeline. So many questions were there, unknown answers, unexplored areas. So we had to refer multiple references, online resources as well, apart from domain experts and lecturers, in understanding what exactly we need to study and what exactly is required. And then why we are doing this data and business understanding. So this was what was the motivation behind certain understanding or study or do knowledge acquisition of stock market, and the rationale as well. So everything was tied down to or tracked back to our business goal of predicting best performing stocks using the available past historical data. So how we perform the knowledge acquisition? So we perform knowledge acquisition using structured interviews by visiting field, that is by Quant Global Investment Company, every weekend actually, and also on the appointments on weekdays, convenient time, and semi-structured interview techniques. That way we were part of acquiring the knowledge, and then the unstructured email, WhatsApp, and phone call and other discussions. So we followed all the possible ways of collecting the or acquiring the knowledge. Once we understand data, we collect data, then we need to be familiarized with the domain or the data or the business associated with the data. So what we followed was we made sure that we follow a formulation of initial set of stock level data which is needed, and then we downloaded the stock data at regular interval time to get familiar with the data. Then we performed a exploratory data analysis to understand the data better, which is also part of the data understanding, which is an iterative process. And then we clean the data. Not all data is required for analysis, so we need to clean, we need to factor the scaling, and then we need to re-engineer our feature selection. We need to derive multiple data points based on the current given data set, and then appropriate scoring, normalization, and relative ranking of stocks by each factor score and grouping into respective portfolio quadrants. Meaning we categorized each available stock market data into multiple factors and then grouped different stock data uh, into multiple portfolio quadrants. We will see what exactly I mean multiple portfolio quadrants. And then we generated a daily factor returns for all portfolio quadrants. For each factor, the best quadrant should preferably perform best over time. So what we did was we tried to group the different data, stock data, into a different format or different groups, and then each group represented a quadrant, and then the best quadrant should preferably perform best over time. That was our assumption. Then we have combined and applied appropriate weightings to each individual factors, then form the broad composite factors. So this is how we represented our domain knowledge. So a typical US stock domain model, it consisted of different types such as knowledge model, that is US stock. The domain knowledge was US stock domain. The domain schema was named as a stock selection schema, and each individual concept was stock list and description and attributes. In attributes there were many different kind of columns. If you consider the database, the attributes formed columns, and then there were multiple derived factors such as sector, whether it was a financial sector or healthcare, industrial, consumer, materials, different types of sector. So there were different kind of symbol, different kind of attributes such as company, symbol, market cap, volume, category, style selection, that is dividend or growth or momentum, price changes for past 10 days, price changes for past 1 month, price changes for past 3 months. So different kind of uh, base as well as derived factors were represented in each domain for each stock symbol. Yeah, so we need to consider overall architecture when we are talking about system architecture, which comprises of the data architecture, the application architecture, the technology, underlying technology architecture, the data flow models, how we are how we are applying our models, and how the results are evaluated and stored back into the database, and the technology component stack, we are going to see that, and also the deployment approach that we are following. So these overall underlying components together form the system architecture. So let's see what are the technology tiers we have used in building this smart trader. First comes the database, and then the application and the presentation layer. So in the database layer, we had used SQL Server 2008 because the sponsoring company was using the enterprise Microsoft SQL Server 2008. In the application tier, for multiple models and algorithms, we used multiple technologies including R, C#, C++, and Python, and of course the SQL language for the exploration of data. And the presentation layer, we used Shiny and Windows Presentation Foundation. So these together formed our technology tiers for the smart trader. So the data modeling methodology we followed, as you know, is CRISM-DM methodology. So we first look at then data understanding, then we looked at the application stack, application architecture, the system architecture, and then we were under data preparation, the strategies that we followed for data preparation. So now comes the model factors. So the objective or variable factor that we have is the future stock returns over a desired holding period such as 20 days. The holding period was chosen as it allows for realistic trading when accounting for costs and system profitability. Other holding periods may also be included as well to see if there might be an optimum holding period inclusive of costs. So then next was the predictive variable and factors. So these factors span across a wide range of explanatory factors for stocks depending on the domain experts knowledge input, and include 6 categories of stock related factors, namely the valuations, the profitability, quality, analyst actions, growth, and technical. So we came up with about approximately 100 factors, which including the forward-looking estimates and historical data. So these factor values will constantly evolve over time as and when we are analyzing the past historical data, stock data. So when we try to analyze, we want to see the best performing stocks and then invest in and gain some value from it. So yeah, so the data preparation stage, the predictive factors. So as you can see here, there are many composite and subcomposite groups for data preparation stage. So we can namely make it as valuations, profitability, quality, analyst function, actions, growth factors, and technicals. Okay. So the data preparation factors mainly is valuations. So we had included fields such as earnings yield, the EBITDA yield, dividend yield, free cash flow yield, sales yield, book yield, EV EBIT yield, EV sales yield, EV free cash flow. So these were the 10 main valuation factors that we considered for each stock symbol per day. And then the profitability factors such as gross margin, net profit margin, earnings, cash flow, asset turnover, capex, and sales ratio. And the quality like debit capital, debit total assets ratio, debit EBITDA ratio, operating cash flow, financing cash flow. So these and the analyst actions, growth, the EPS future long term, the growth rate, EPS past trend, and the sales past trend, the net profit margin past trend, technicals, past price trend and slope analysis factors, past price slope, standard ratio, price momentum, money flow, price for every week, the highest price, the lowest price for per week, and the price from 200 days moving average weeks. So these are many technical factors. So as you can see, after we understand the business goals and the domain knowledge acquisition, we were able to come up with these predictive factors. So this was a domain understanding and business data understanding was, as we say, is one of the important aspect of CRISM-DM. This is why, because the more we understand the data and the business, the better we come up with the predictive factors, and then the better performing will be our models that we build. So we spent about 3 to 4 months to come up at this stage, to come up with these predictive factors. So we call it data rehearsal, but it is actually part of the data preparation phase of the CRISM-DM methodology. So the initial steps was the data files were containing stock level information will be downloaded. We downloaded historically on a daily basis for a period of 10 years from 2004 to 2013. As you can see, the data files containing stock level information were downloaded historically on a daily basis for a period of 10 years, meaning 365 into 10, that is 3650 files per stock. And then the factor values that we saw in the previous slide that were evolving over time, and the predictive models would be applied consistently over time but will dynamically evolve due to time varying factor values. So we started applying these predictive models from 2004 year onwards. So over the time, these predictive models results and derived factors would evolve over time, and the models will be created at least on a monthly basis, so say at the end of each month per year, and the daily weekly models will be ideal if the computing power permits. So actually we eventually we managed to build weekly models using the thanks to the sponsoring company for coming up with weekly models, allowing us to come up with the weekly models, and then the models will be evaluated for their accuracy and return profile over time. So this was the data rehearsal, the initial steps that we followed, and this was the approach that we wanted to take consistently for all the data between 2004 and 2013. So under the part of data rehearsal, still we are doing data exploration and pre-processing. So summary statistics were created for various market capitalizations, that is large, medium and small market capitalizations, and separately for all the 10 sectors that we had identified, like technology, medical, manufacturing. So we had grouped into 10 different sectors. The summary of statistics included mean, median, maximum, minimum, standard deviation, median absolute deviation, percentage with NAs, missing values, lower and upper limits based on a median absolute deviation. This was done every day and it was stored in the database. Various summary plots for all the factors were also created on a single day. They included box plots, QQ plots, histograms, cumulative density plots. So this is very important for analyzing the data, to understand the data, to explore the data. By doing so, this allowed us to better understand the characteristics of various stocks in our universe, which was S&P 1500. So just to summarize, so what we did was, in part of data exploration, we first came up with summary statistics for various market capitalizations separately for all the 10 sectors. The summary statistics contained mean, median, maximum, minimum, standard deviation, median, absolute deviation, and percentages of these statistics for all the stock symbols. This was done on every day and the results were stored back in the database. So various summary plots for all factors were also created on a single day. Then they included box plots, QQ plots, histograms and cumulative density plots for each of these summary plots. So by doing so, we were able to understand better the characteristics of various stocks in the universe. So as you can see, for a single factor, using a box plot we are able to describe the summary statistics. This is a normal QQ plot. This is a bar graph. This is a normal curve graph. So similarly, actually this stock is actually earnings yield. Okay, on Jan 2004 as well. So this earnings field FY1 factor, we are able to understand the data better. The mean was 0.04, the median was 0.04, the maximum for this factor was 0.16, and the standard deviation was 0.04. So these kind of statistics for all the different factors were stored in the database. So as part of the data exploration and pre-processing, which we call the major step of data rehearsal, there are many missing values. So as you can see, for the valuation factors for various market capitalizations for the year 2004, the average percentage of missing values was for earnings yield FY1 stock factor, the large capital market, it was about 10% and missing values, and it was about 30% for the small capitals, and the dividend or the sales yield also had a similar ratio. That is, for the small capitalization market, it was around 60% of the missing data for the dividend yield, and about 45% of the sales data for small cap for the sales yield. So the smaller the market cap of a stock, the more missing values there are. Small cap names omitted for consideration due to lack of data and liquidity concerns. So these missing values, how we approach missing values depends. If the missing values are having a minimal impact on the performance of our model, then we can omit it. But if the missing values, if we remove the missing values, if it is playing an important role, then we try to replace the missing values with the average value, other imputation techniques. But for our case, for the smaller the market cap of the stock, the more missing values there were. So the small cap names omitted for consideration due to lack of data and liquidity concerns. Then comes the next process. How do we handle outliers or the missing values in the data exploration and pre-processing stage? So we had to follow an uniform approach which was applied to handling outliers and missing values. Handling outliers. Outliers are actually defined as, which we defined as being 3 median absolute deviations above or below the median and are restricted within these limits. And meaning we actually omitted the outliers whose median absolute deviations were 3 times above or the median below the actual standard median, and we started analyzing the results only in these restricted limits. Handling the missing values, actually we removed the stocks certain percentage of unavailable values on any day. A threshold of 30% was set, and then we remove the input variables where much of the data is unavailable. A threshold of 30% was again used to determine this value. In some cases, we impute the missing values of the input variables to equal to the median. So these were the different approaches that was followed in the data exploration and pre-processing while handling outliers and missing values, and these decisions were taken under constant guidance and input from the domain experts. And then comes normalizing the input variables. So the stocks from different sectors usually have some differences in terms of factor distributions and performance. For example, for a factor variable such as debit capital ratio, the telecommunications or the utility sector will have a higher average value compared to other sectors as they are more capital intensive. The technology sector, on the other hand, is less capital intensive and hence has less debit. Z-score was the method to use or normalize the input variables after handling for outliers and missing values. So the normalized resulting values would be in the range from -3 to +3. So as an illustration, illustrating factor differences across sectors in the year 2010. If you see the debit capital ratio percentage, consumer discretionary has 32%, utility is over 54%, telecommunication is reaching 60%. If you see the dividend yield FY1 factor, the consumer is about 1%, consumer products discretionary, whereas the utilities and the telecommunications have been above 3.8%. So the normalization would be required in these cases. After the handling of outliers and missing variables, and after normalizing the input parameters or the values, now we have to select the factors. So this slide we will go through about determining the factor returns. On any trading day, we use normalized factor data and rank values for each factor for each stock in ascending or descending order. So we will buy stocks with normalized values which are greater than 0 and sell short stocks that have normalized values less than 0 for factors where experience tells us that the higher the value, it is better. For example, for a factor like earnings yield, generally the higher value, the better the returns. So we use the 1-day forward return and determine an average return based on the difference between the average return of stocks being bought and the average return of stock being shorted. So this process was carried out every day and the resulting daily spread returns are linked together to form a cumulative return series for that factor. As you can see here, the more the constant increase in the gains for the period of time, it is considered as fantastic factor. And there are also the case where neither good nor bad factors, like mean reverting implies like faster alpha decay, higher trading costs, the variation is a lot per year, and bad factor best to avoid, good to study if the reversion is event is based. And the last one was good factor which needs to be inverted, that is this by profit, this may be not a good factor but this is following a trend. So this, with using this trend we can determine whether this is a good stock or a bad stock, good performing stock or a bad performing stock. So that's why for analysis purpose this is a good factor, but we need to invert, so we had inverted values for this. So we actually defined profitability as annual return divided by annual volatility. So consistency and stability of profitability after adjusting for volatility. So these were the determining factors. So this is how we decided whether a stock is performing better or not. So we least narrowed down to 31 factors now. So from 100 factors we narrowed down to 31 factors using risk adjusted return of long and short portfolio. So once we are okay with the data, then we had to devise specific data models, that is devise specific data models that adapt to stock characteristics and market conditions, which may lead to better performance. So moving window, this was a combination of short and medium term windows from 1 month and 12 months for training and testing data. Okay. And sector differentiation means different characteristics of stock due to the sector which is belongs to, which it is in, may warrant the use of sector based models. Seasonal differentiation, stocks can behave quite differently during different months of the year. So possibility of creating and training 12 separate models for each month across a period, say from 2004 to 2010 or 2004 to 2009. So we can differentiate using seasons. So moving window, sector differentiation, seasonal differentiation, there are many different uh, ways which we can define the stock characteristics. Now, now comes after the data preparation and data rehearsal. So we went through business understanding, data preparation till now. Now comes the modeling, pre-modeling, algorithms and evaluation stage. So this is our model structure actually. Classification model under which, so weighted window based modeling and cluster based modeling. Under weighted window based modeling, we use a support vector machine, random forest, AdaBoost and neural networks. And cluster based modeling, also we use support vector machine and random forest and AdaBoost. So Windows partitioning weightage. So what exactly it is? So in the Windows weighted window based modeling, so our approach was actually weighted windowing actually aims to expand the data to look back as an attempt to gain the insight and pattern in the time series and therefore hopefully achieve better performance. Each window will build a model and these models will be assembled to product the resultant prediction via voting mechanism. The system creates models from 4 windows actually. Each window is associated with a certain weightage. Generally, the more recent, the more weight is assigned. This reflects the essential trading fact. Short-term fluctuation momentums have higher impacts for trading decision. That is, short-term fluctuation momentums have higher impacts for trading decision. So this was the mechanism or the thought process behind windowing, partitioning and applying a weightage to each window. In the clustering based modeling design, so for each end of the month, we try to build a cluster with the past 1 year, past 3 year, past 5 year, past 10 year and gave them equal weight for all. And then we used a mean, median, mode to aggregate daily sector data. This was tested on 2014 end of the months. So what exactly it is? So let's have a look at what was the difference between weighted window and clustering comparison. So actually the purpose for both the approaches was to endeavor to achieve better performance by extending the look back approach in the weighted window in the dataset, and in the hope to gain more insight of the patterns. The rationale was both belong to compositional hybrid modeling, and submodels are actually mutually exclusive for cluster-based model but mutually complementary for weighted weights window model. Selection of training dates. Weighted window based models uses the whole past 1 month, 3 month, 6 month, 12 month as different windows, whereas the clustering based model finds the cluster with the test date among the past 1, 3, 5 and 10 years group. Modeling and testing is the same for both weighted window and clustering methods. So this was the general process flow that we followed for the models. So the scored data after the data preparation phase was put under a feature selection engine, and the feature selection engine split the data into training data and the testing data. First, the training data was we did the data meaning, and then we trained the models and did the prediction. And then on the testing data, we tried to compare with the actual results, and then the error rate was compared, and then the prediction was done with the error coefficient as well. So the only difference between the training and testing data was the testing data had a feedback loop of error coefficient. We were trying to compare the prediction rates from the actual results, stock market results. So this was the measurement criteria. The measurement criteria was accuracy, precision. So the mean of returns if bought all the predictive positives, and in addition the sensitivity, specificity are also measured for measurement comprehensiveness. So accuracy, precision, sensitivity and specificity is the major measurement criteria for performance of the models. So yes, support vector model or support vector machine. So why support vector machine model? SVMs can be a useful tool for trading applicants when non-regulatory data exist in the data, that is when the data are not regularly distributed or have an unknown distribution. This can be the case when stock level metrics changes. So some advantages of SVM technique include elegancy to tackle non-regulatory distribution in stock trading context. So by introducing the kernel, SVMs is flexible in the choice of the type of the threshold separating factors, separating good and bad companies, which may not be linear all the time. As the kernel implicitly contains a nonlinear transformation, no assumptions about the functional form of the transformation, which makes the data linearly separable, is necessary. The transformation is based on a robust theoretical basis without the need for human expertise judgment. And also they provide a good out of sample generalization given the parameters C and R in the case of Gaussian kernel, which are if we choose appropriately, then appropriate generalization grade can be achieved, and SEMs can be a very robust tool even when the training sample has some bias. SVMs deliver a unique solution since the optimality problem is convex. This is the advantage compared to other models, especially neural networks, which have multiple solutions associated with local minimal and for this reason may not be robust over different samples. So we use normalized factor score itself as the input and the normalized 1 month forward return as the output. The normalization is done across each factor, that is stock factor, of each sector on each day of the available stocks. We then assemble this data across the past 3 months before the current month end of the data used for prediction. So we set the stocks in the top 20% measured by 1 month forward return as the outperformers, where we labeled as 1, and similarly we set the remaining stocks as 0. So we perform this labeling exercise as 1 and 0, that is best top 20 performing stocks are labeled as 1 and other stocks are labeled as 0 on a monthly basis, and pile the previous 3 months data together as training data. So we did this in R actually, R language. So the algorithm was implemented in R using the kernel lab library. Some of the parameters were the kernel was a radial basis function and the C constant was taken as 1. So at the end of each calendar month between April 2004 to October 2014, that is more than 10.5 years of data, the model is fitted to the available stocks in each sector to predict the likely performing stocks. So here we had used 3-month moving window for the support vector machine. So the next model is a random forest modeling approach, random forest or RF. The random forest technique is based on ensemble learning of the decision tree or collection of decision trees. Ensemble learning is useful for improving model accuracy with the integration of multiple decision trees. Random forests differ from decision tree in that they use a modified tree learning algorithm that selects at each candidate split in the learning process a random subset of the features actually. So if some features are very good predictors for the target variable, these features will be selected in many of the resulting trees, hence potentially increasing predictive ability than using a single decision tree. So random forest has some of the features such as it can deal with high dimensional data. It allows the user to estimate the importance of each variable. Variables are randomly selected at each node of a tree, which provides a better classification compared to a single tree. It stops growing the tree when the number of nodes reach a certain threshold. So we set the stocks in the top 20% measured by 1 month forward return as the outperformers and labeled it as 1, and the other stocks which are not in 20% of the performance, we set the stocks as 0. So we perform this labeling exercise on a monthly basis and pile the previous 3 months data together as training data. So we chose only the 3-month window due to the speed and size limitation of the learning algorithm, which was written in R. So the algorithm was implemented in R using random forest library. Some of the parameters were like the number of trees we allowed to grow to 500 and number of predictors that sampled for splitting of each node was around about 14. So at the end of the calendar month, each calendar month between from April 2004 to October 2014, for about 10 years and 6 months of data, the model is fitted to the available stocks in each sector to predict the likely performing stocks. So we use the 3-month window. So next is AdaBoost model, AdaBoost modeling. So we used a classification technique, one of the classification techniques using AdaBoost. Actually, the machine learning methods have become more and more popular in the quant world to predict stock returns. The main idea in using machine learning methods to predict future stock returns is to automatically learn to recognize complex data patterns and capture the hidden relationships among financial data, which are normally difficult to see with the human eye. So the AdaBoost model treats stock selection as a binary classification problem using supervised learning. We classify the stocks in our universe into outperformers and underperformers based on 1 month forward stock returns. The construction of the confidence score has two steps: the training step and the prediction step. In the training step, we use the end of the month factor scores for each stock and 1 month forward returns as the training data to build the classifiers. In the prediction step, we use the current month factor score as the input for classifiers. We build the training step and output is the confidence score. So we use cross selection of ranking of factors rather than the factor score itself as the input, and calculate the factor ranking each month. So the way we explain algorithm is, we normalize the factor value to a real value 0, 1 according to the rank of the factor for each month. Then we classify the outperformers and underperformers. Then initially duly weight each stock. Then we build the weak classifiers for each factor and then add the selected weak classifier to the strong classifier and update the weights. Lower the weight for correctly classified samples and increase the weight for the wrongly classified samples. So in this way we try use AdaBoost algorithm to classify stock as weak classifier and strong classifier. So weak performer and strong performer. And this process of building the classifiers is repeated until we get the we process all the data. And the final output of the strong classifier is the value of all the weak classifiers added up together. So we able to classify. So in detail we'll see the binary classification. So the AdaBoost model treats a stock selection as a binary classification problem as mentioned before, which uses a supervised learning. We are calling it a supervised learning because we are already classifying the data into 1 or 0, the outperformer or the underperformer, based on 1 month forward stock returns. So in the training step there are two things. In the training step we use the end of the month factor for each stock and 1 month forward returns as training data to build the classifiers. In the testing step, that is the prediction step, we use the current month factor score as the input for the classifier. We built in the training step and output will be the confidence score. So when we see the data refinement or data fitting, the cross-sectional rankings, so we actually calculate a factor of ranking for each month for all the available stocks. Then we normalize this factor to rank between 0 and 1. So the stock in the top n percentage are outperformers, they are labeled 1, and the stocks in the bottom percentage are underperformers. So the labeling exercise is on a monthly basis, and then finally pile the different months data together as available. Next is neural network. So this is a normal neural network. Actually, as a computational model, the neural network features as like modeling of the actual brain. So it has n number of inputs and middle layers, and the target is the output. So we used an input layer of 32 nodes representing the collective input data and the bias, and the hidden layer around 16 nodes for the layer 1 representing the compositional factors of the stock data, and then the layer 2 was around 7 nodes representing the sig aggregative factors and bias as well. So the output layer was the one. The activation function used was bipolar sigmoid function, and the learning technique was back propagation technique. So neural network with four predefined windows, four classification models were built and combined into a composite model with a majority win voting mechanism, as you can see here. And we did this in using C# language. So in our modeling approach of neural network, we followed two approaches: classification model to predict the stock price fluctuation trend either up or down, and the regression model to predict the stock price fluctuation amplitude and the quantity. As a rationale, the computational model neural network takes long training time with large training data. Still, with the NN architecture which was defined before, instead of using back propagation learning to fine tune the weights of the neurons, genetic algorithm which is capable to generate optimization solution generally and globally is incorporated to optimize the weights as an attempt to accomplish better predictability in a shorter converging time. Okay, so after the brief introduction or brief details about the different models used, let's look at the next stage, that is deployment. So this was a data flow model that we seen earlier. So as you can see here, there's a market data server which was source for all the stock data, historical stock data from 2004 till 2014. So we written Python scripts to download the data and then dump into the database. So once we had the database, so we ran four different modeling techniques which we discussed earlier: the random forest based modeling, SVM based modeling, neural network based modeling, AdaBoost based modeling. All the results were analyzed and calculated and then stored back into the database. And we had built a client using Shiny and Windows Presentation Foundation like WPF GUI, which will retrieve the results from the database and show it to the user in the front end. So let's look at the software component stack. So this all comes under deployment. So the repository layer or the database layer had a data importing component which will import the data from the stock market live data from the internet APIs, and the data accessing component is a component that is that helps us retrieve and store the data from the application layer. So application layer had an inferential engine component which will run different models and then store the data as a result into the database. Data intelligence enablement component, which is actually the actual models that we built. User investment profiling component is a small subset of user profiles who prefer to analyze data depending on the different markets like technology sector, utility sector, consumer product sector, etc. And factoring the analytical component, computation component is actually again the modeling scripts. Then comes the presentation layer, which is interactive graphical user interface where user can input the collection, validation, representation, transformation component values. I will show you the sample UI in the next few slides. So yeah, this is the application deployment. The database was RDBMS. Application layer stack was Python, C Sharp, R, depending on the functionality. Presentation layer was in R, and Windows presentation layer. So this is the system snapshot, where in the left side you can see the user can select an year and month for which he wants to see the best performing stocks, and then he can see the can select the sectors: consumer discretionary, consumer staples, energy, utilities, telecommunication, etc., etc. And he can also select the model, which model he wants to see. So the right side is the portfolio recommendation. Actually, it will not only show the top performing stock or the sector in the recommendation. It will also to show the accuracy, sensitivity, specificity, and precision. So using AdaBoost algorithm, in this example, in the blue color, using AdaBoost algorithm, the top sector was consumer discretionary sector with the Aaron Zinc, Advanced, Botpods by big lots. So these are the companies, top and performing companies. With the neural network, for the same dataset, consumer discretionary sector, these were the top performing stocks. Using a random forest, again it was consumer discretionary. So different models were giving different sectors as output, but out of which consumer discretionary is common factor. One more thing we can say, the flexibility to use multiple models is left to the end user as well. So if user doesn't want to select, he can select all and keep it start. Or if a user is interested in only particular like neural network or random forest for the highest accuracy and all, because you can see random forest accuracy is 0.77, that is 77% accurate. So in that case you can only select the random forest and then click on start. It will again reanalyze and only show the random forest related or any model selected output. So the conclusion and discussions. So what were the conclusion and discussions? The project was completed in accordance to the requirements from the company as well as the requirement from our master's degree. So we were able to provide value to the sponsor organization by providing this smart trader tool, and the experience was very good. The experience was we were able to build a knowledge based system using common cats, CRISM-DM, and computation intelligent and knowledge engineering techniques in practice for the stock trading and financial industry. And we were able to do a collaboration with the sponsor organization to achieve the common goals, the business goals. That's the most important thing. And yeah, we learned a lot, we enjoyed, and the fruitfulness of this project was very good. So this are some of the real life trading assumptions. So a new portfolio for each method is created on the first weekday of each month based on the data for the last weekday of previous month. So all trading is assumed to be done at the price close of the first weekday of each month. So trading cost is assumed to be 0.15% of the trading turnover. So trading turnover assumes both additions and deletions to the portfolio, that is maximum 200%. If predicted names are similar for new month, portfolio is held till the next month, meaning if the predictions are repeating from the previous month to current month, then we will still keep that same portfolio. Various statistics such as return net of costs, number of stocks traded, and turnover are calculated on a daily basis over time. The performance based statistics such as Annualized return, volatility, Sharpe ratio, drawdown are derived for each year and across time. So these were the absolute return and volatility of our performance of the stock rate. As you can see, except for the year 2008, the absolute return, which was in negative because of the external conditions which resulted in stock market down value. As you can see, the return was using different models. ADA boost in 2018 it was minus 35%, but as you can see in 2013 using our tool we could make 36% profit returns using ADA boost predictions, and using random forest also it was 36% returns. If we use ensemble and it was 25%. So except for the so different algorithms were mostly accurate. Volatility, if you study the volatility also it was different values indicate most of the algorithms actually performing nearby, like ADA boost, SVM, neural network and random forest all were relatively close to each other. Next is if we take these are some average drawdown. These are different analysis of the results actually. The comparison of different performance of smart trader over different years from 2005 to 2014. So this is mean across 2005 to 2014. Max drawn, average drawn, volatility, return, Sharpe. So this is cumulative daily performance net of costs actually according to different algorithms. For this we use Tableau for visualization. So the blue line is the Adabush algorithm. So as you can see, if we use Adabush algorithm as per the diagram, it is more consistent and the cumulative daily performance is better. The gain would be better if we use the sorry, this is not Adabush algorithm, it's ensemble. Ensemble is the most powerful technique, that is best of all. So here are some reflections. So using CRISM-DM methodology, we built Smart Trader. So it illustrates that the machine learning techniques can, when used appropriately, has the ability to select stocks that outperform the general market after cost over a long duration. However, at any stage in time, they may end up selecting stocks that do not perform well due to changes in the market conditions and cause returns to be unstable between the periods. So the external conditions which affect the stock market may not be included in the machine learning techniques. It takes into consideration the possibly non-linear nature of explanatory factors such as well as interaction between factors in influencing forward returns. Using risk-adjusted return as the target factor can be a possible enhancement in the future. Complementary approach to linear factor-independent approaches used by quant for stock selection. So we used hybrid programming actually because it was showing strength and weakness for each actually. For example, R is great for prototyping, working with data, but a bit slow compared to C Sharp, C++. But it is harder to code data science related algorithms in C++ and C Sharp. We had suggested that PyQuant may consider using more efficient programming tools wherever possible so the testing strategies iteratively can be carried out faster. So yeah, now I just want to summarize of the CRISM-DM methodologies. So as we can see, business understanding, data preparation took bulk of the time for the project, where we try to outline the determine the business objectives in the business understanding, and then did the assessment, situation assessment, and what are the data mining goals, and what is the project plan. All this was discussed in the business understanding phase. Once we were okay with the business understanding, then we went to data understanding, where we collected the initial data using Python scripts. All the stock data was collected for the year 2004 to 2014, and then we did the exploratory data analysis by analyzing different data stock data factors. Top 100 risk factors were taken, data point factors were taken after the domain knowledge acquisition. Once that was done, then we prepared the data, that is we did the feature engineering, selected the top 88 performing indicators, and then that included selecting the data, constructing the data, transforming, feature engineering and formatting, and then storing the results back to the database. Once that is done, we model the data using Adaboost algorithm, random forest, support vector machine, and neural network using windowing approach. So then the results from these models were assessed, analyzed, stored for the evaluation stage. So once we got to know that we cannot single-handedly choose a single model for our prediction of best performing stocks, we used an ensemble, that is a combination of all of the models results, and then use that to recommend top performing stocks. Once that is done, then we went to the deployment stage, where we deployed all the application, presentation, as well as the backend database layers, and then consumed by the users. So this was the summary of CRISP-DM, a walkthrough via a sample project. Reached end of the session. So we have to partly cover data analytics overview, knowledge discovery, data mining techniques, CRISP-DM methodology, and today we have covered CRISP-DM walkthrough with example project end to end. So thank you again NUS PAC team for allowing me and its members for allowing me to share this session with you guys. Please send your feedback and queries to sriranga.kulkarni@gmail.com, or alternatively you can contact me or connect me on my LinkedIn profile. See you next time. Thank you.